So that's it from my side. Now let's get started with the very first session. For the speakers are Julia as well as Shrishti. And do note that our next session will be on February 23rd, same time. And that's where we'll be talking about regression and classification. So the speakers for that session will be Julia as well as Deepshikha. All right, thank you so much. And I think we can get started with our presentation. So over to you, Shrishti.
Hey, hi everyone, and I'm also a volunteer here at Women of Code, and so I'm really excited to present this as it is my first time. And thank you, Women of Code, for giving me this opportunity. So Sneha, let's move on to next slide. Okay, so this is a very beginner session. So everyone, we hope that will be comfortable with this session, and here we'll be covering the very basics of machine learning, and this is a complete theoretical session, so it will be easy for us to grasp. Okay, so let's start with the what is ML. Any idea, guys? Like, the term itself is quite explanatory, so if you can drop any guesses on the chat, like what is ML? Teaching machines to learn. Okay, any more guesses? Okay, next slide, Sneha, please. Yeah, so machine learning is basically a subset of artificial intelligence, and it basically is like you can think of it as teaching a child what is A, B, C, D. Yeah, you give certain examples like how A is written. You can explain that child, yeah, A is written in caps like this, or it's written in small letters like this. And similarly, you keep on giving them examples of what A looks like. And then once you ask that child, like, what is A, he can hopefully tell you that this way you can write A. So it's a very layman's example to uh, learn like what ML is. So it's basically we write algorithms in such a way that they can just predict with the historical data. They learn from the historical data and they can predict outcomes that is very useful for businesses. So as you can see here on the slide, it focuses on the use of data and algorithms to imitate the way that humans learn, gradually improving its accuracy. They can learn without being explicitly programmed, and they can generate their own algorithms, and all of this is automated. We don't really program or write instructions for the machine that you have to perform in that particular way, but we generally allow the machine to find patterns on its own. So what ML is. Next slide, please, Sam. Okay, this will give you more clarity how traditional programming is different from machine learning. If you have previously been coding, you will see that you are actually writing all the rules and telling the algorithm like explicitly, like you have to do this based on what these are the conditions, and you have to perform in a specific way to give a certain output. It's a totally manual process, and the rules and the logic, that is all of this is defined by us when we write that particular program. But machine learning, we don't do that. We do quite the opposite. We just give the data, we tell that we need this output, and the machine tries to find out the patterns. It tries to make rules on its own so that it can predict the output. Next slide. Yeah, this slide will answer most of your questions. If you can relate, this is how we actually been coding earlier. We give the rules, we give the data, and we tell them that this is what we have to look for, the answers, and we write the rules. But machine learning is on the boom right now, and it is actually easy. The algorithms are quite easier, and more uh, efforts are needed before applying the algorithms. So ML is very easy, and it's a lot of fun when you try to learn the algorithms, and it's complete maths and statistics. It's a mix of all of that. So it's just that you give the answers, you give the data, and the machine tries to learn the patterns in that data and tries to figure out how to predict the answers that we have already told the machine that this is how we want. Yeah, next slide. Okay, so yeah, this is a very confusing slide, by the way. AI versus ML versus DL and data science. So let's start from the top. What is artificial intelligence? So you can think of artificial intelligence like human intelligence. It's just that we are trying to imitate human intelligence via machines. So it's like simulating human cognitive uh, thinking, and it basically is a it gives the ability to the machines to perform in a certain way, to think in a certain way. And machine learning is a subset of it because it gives uh, it the like this is what it gives the AI that you have to do it in this manner. And deep learning is a more advanced version of machine learning. We move into neural networks and all. So that comes later after you've completed machine learning. And what is data science? So data science, you can think of it as uh, basically deals with the science of data. It's like it uses AI, it uses machine learning and deep learning, all of that, just to make sense out of the data that we have. So if there are any questions like related to what AI, MLDL, or data science is, you can ping in the chat. We can pick up from here. Are there any questions? Okay. Data science is not same as data analysis. I'd say data analysis is a part of data science because that is what I explained to you earlier. Because machine learning, it's like it comes after the analysis part. After you've explored what data is, what are the hidden patterns, how you like what you call exploratory data analysis. After that, machine learning comes after. So data analysis is a part of data science, and these are two different fields. For data science, you need to know all of these algorithms and all. For analysis, it's not necessary because analysis is more on you have to look for patterns inside the data, what the data is telling you about, all finding like you can, one example could be descriptive statistics, what we do in analysis. And that is what gives us more information on what the data is trying to tell us. Okay,
Sorry,
I
before you
think we can
continue,
move on.
sorry, just a second. Sorry to interrupt you. Before you continue, there are some really good questions in the chat. Would be really great if you guys could ask it in the Q&A box, because there's a chance that we may miss your questions if you ask that in the chat. So I request everyone to please ask your wonderful questions in the Q&A box. Thank you so much.
Okay, uh, deep learning and machine learning, I'd say machine learning is, you can say, part one, and deep learning is a more advanced version of machine learning because in deep learning we actually use more advanced algorithms, and sometimes when we have more features in a data, which the normal ML algorithms can't. We can't use normal ML algorithms for those scenarios. We actually switch to deep learning, and it's just a advanced version, you could say. That's it, I think. Sneha, can we move on?
Yeah, sure.
Okay. So let's discuss like what are the types of machine learning. So there are three categories of machine learning: supervised learning, unsupervised learning, and reinforcement learning. So when we move on, when we think of supervised learning, it's like, from the term itself, you can say that we uh, train the model or the algorithm, everything. Like it's like feeding everything. Like this is this. We tell them that, suppose we give them 3 4 images of dogs, different, like a dog sitting or a dog barking or a dog eating, and we tell the machine that this is a dog, and several other image examples of a dog, and that is how the machine learns. Yeah, this is a dog. That is how the algorithm is written, and it is programmed. And after, like, given some different data that is different from what we have trained the machine, the machine successfully, with the not exactly 100% probability that it will give the correct output, that yes, this is a dog, but definitely it will give uh, the correct output. Can you move to the next slides now? Yeah, exactly, Echo. Just like how you teach a child, it supervised learning, it's very similar to how you teach a child. So basically, this is what we do in a supervised learning. To the algorithm, we provide the data set, a data that is properly labeled. We give this labeled data set to the machine, and then we allow the machine to learn that based on, and we tell the machine that these are the features, and this is the target variable. That is you have to predict this target from the features that we have given to the machine, that these are the features that you have to learn from, and you have to predict this target. So a set of target variable and a set of features, this complete data set, we give it to the machine, and we allow the machine to learn from it. That and the classic examples you can say here are email spam classification and stock price prediction. Basically, supervised learning is further divided in two categories, which is regression and classification. So classification is mostly, you can say, based on categorical data. It's like, is it, if we see this example only, email spam classification, it's like, is the email a spam email or not? 1 or 0, yes or no. It's like, you can say, there's a category, it's not a continuous value, it's a discrete, and basically it's a category. And in regression, we use it when we have continuous data. Basically, you can say the target variable, it's you have to predict the price, sales price, it could be the stock price, it could be anything. So the main idea behind supervised learning is, you give a label data set, telling the machine that this is the data set, these are the features that you have to learn from to predict from this set of target variable. And then based on what the target variable is, like, is it a continuous, or is it a category, like yes or no, or is it a continuous value, or continuous data type, the data type of that target variable is continuous. Based on that, you can decide what type of algorithm, what type of supervised algorithm you will use. Will it be a classification model, or will it be a regression model? So based on that, you choose, and then the implementation is the same. Let's any question, guys?
So I think there are a few questions asking the difference between supervised and unsupervised learning. So if you could perhaps elaborate on that one, Shrishti.
Okay, I think let's discuss all the three first, and then ask questions. Let's like pick up questions after that. Okay, let's move. Okay, this one. You can see here. The first, sorry, the column B, C, D, and E. The For a supervised learning, these four columns will be served as features from which the data will learn that okay, that of the 5.1 sepal length, 3.5 sepal width, and so on is an iris setosa. Is it's The species type is setosa, and similarly, if you'll see that different set of values will give a species as uh, virginica, and there's one more category. So basically, you will give a part of this data as a training set to the machine, telling them that this is the feature and the target variable is species here. So based on the four columns, the sepal length, width, petal length, and width, it will learn that okay, certain type of values have species setosa, the others have virginica, and so on. So this is how it will learn. And then if you'll provide a new data based similar new data, it will try it will accurately predict that whether it's a setosa, it's a virginica, or vesicle. Let's move to unsupervised learning. Okay, so unsupervised learning, it's just that here we again give the data set, but it is not labeled. We will not tell the machine that this is the target variable. Here the machine tries its own to figure out what are the hidden patterns. It tries to you can say it tries to cluster together. It tries to find the similarity between groups of data and tries to cluster together those which have the high similarity, and it tries to decluster those that have the high dissimilarity. And we use different types of algorithms to decide the similarity and dissimilarity uh, distance. And okay, so uh, okay, so here it says that it explores the data and it describes hidden structures or the unknown patterns from the unlabeled data. Here there are two types of unsupervised learning. One is clustering and one is association. The clustering one, as I explained you, it's like you can give them some photos of cats, some photos of dogs, all with different, not exactly the same photos, but it could be a cat running or a cat sitting and a dog eating and a dog barking, and similarly different kinds of animals. So it will try to judge from these images that yeah, these 4 5 uh, images are of cats, so it will try to cluster these cats because these look similar. It will try to cluster the dogs photos into another group because these look similar. That is the main idea behind unsupervised learning. The other is association. Here you can think of it as if you go into a supermarket, it's just as it says, buying habits of people. So people who buy X tends to buy Y in a shop. You can think of it as how supermarkets use the uh, customer purchase behavior to just think of how customer really purchases from their store. It's like a customer who tends to buy milk bottles also buys diapers. So it's like maybe they have infants and in their home. So maybe this is kind of an association. So there's a proper algorithm behind how association algorithm works. So that is beyond this beyond the scope of this session. But it's the gist of this association is it tries to look for association between basically used in this example only, buying habits of people, to just to get more insights from customer purchase behavior. Next slide. Okay, so this is the same data set that we're using, but here you see we have not given the target variable. Uh, Here we have just given the features, and the machine itself will try to figure out the similarity between the data, and it will cluster together, and it will make three groups based on setosa, virginica, and versicolor. And that way you will know that yeah, there are three species of flowers in this data set. Next slide. Okay, this is reinforcement learning is completely different from the other two that we've discussed. And it's like here we don't exactly need a data set. It's like maybe you can think of it as a reward and a penalty based learning. And the model learns from a series of action to perform a task, and each of these action, whatever the machine performs, it will get either a reward or a penalty. So the main goal of the algorithm is to uh, increase the reward. I mean, the more, if the error is high, then the penalty is high. It's the main goal of the algorithm is to keep the score high. So the example we can take it as training a dog to sit with a biscuit as a reward. It's like we don't we don't actually uh, give any data to the dog, right? It's like when we you can say we are trying to trying the the dog to eat. We are trying like giving a biscuit to the dog and letting him like if he can eat or not, or any other task. Like if it's just, let's take an example, like we're throwing a stick and the dog has to go and pick that stick from its mouth and come back. So if he does that successfully, he will get a biscuit, and if he does not, he will not get a biscuit. It's like that. So the reward would be that he will get a biscuit if he goes and pick up the stick and comes back, and if he does not do that, he will not get that. So basically the dog is a machine, and he learns it with this experience that yeah, he is getting a biscuit only after going after the stick, picking it up from its mouth and coming back. This is how the algorithm works. Okay. Now if there are any questions, we can pick one by one. Okay, what is the difference between clustering and association? Okay, so firstly I'll pick this up. See, clustering and association are two different algorithms, and clustering is basically finding similarities which set of records are similar to one another. You can say it's if I go further, it is like diving deep into the algorithm, but it's like calculating the distance between. There are different methods for calculating this dissimilarity and similarity distance, with which we actually calculate this. Uh, this is actually how clustering works. So the group of data with the less similarity score is declustered, and with more similarity score, it is clustered together. And association is like uh, thinking, think of it as uh, the best example is that customer purchase behavior only. It's like if you go in a store and you tend to buy milk bottles with the diaper. So if more and more customers do that, so what actually uh, the supermarkets do is they tend to align their uh, the diaper section and the milk bottle sections may be close to each other, because what they have learned from the previous data is that mostly customers who buy milk bottles tend to buy diapers. So what they do is uh, like they try to like align these sections next to each other, and so that even if just to check if it's working for all customers, or maybe what segment of customers are actually uh, picking up big bottles and diapers. So that is just how it works. That's the gist of it. Okay, what algorithms are used for? And uh, Sneha, would you like to take this question up?
Sorry, which one?
This one. Uh, how do you reward a computer? And the next one.
Yeah, okay. Actually, I was just typing the previous question, so maybe I'll just take it in that order. So Emily asked, how do you know what type of learning to use based on your main goals? So Emily, basically, now if you have unlabeled data, that is you don't know what your data is, like you just have some random data, and you basically want the machine itself to find out the similarity in this data. In that case, you use unsupervised learning, because you have yourself not labeled this data. You just have data, you just have some data, and you want the machine to find the similarity in this data and group it or cluster it together. So in that case, use unsupervised learning. So if that's your goal, you'll be using unsupervised learning there. Now, suppose you do have labeled data. That is, let me give you an example. So if you have, like, let's say you have data of two colors, red and blue. So you already know that red and blue, and you know what is red, you know what is blue. And when you're feeding it to the machine as well, you know that you're feeding red in this manner, blue in this manner. So you know what outcome you want, and you basically just want the machine to learn well enough to predict this outcome. In that case, you will be using supervised learning. Now, suppose you do not want this type of data. You do not want any labeled data. You don't want any unlabeled data. You just have a model and you want a very human-like learning. So how do we humans learn? When we start out somewhere, we start exploring and experimenting a field. We make a lot of mistakes. We get scolded for our mistakes, but these scolds and these mistakes that we make, we learn from them, and then we go in the right path. So that is exactly what reinforcement learning is. It's used a lot in the game development area or gaming area. So when you have a game and when you're playing that, suppose you make a wrong move, you lose some points, and when you make the right move, you gain some points. So you can think of this as a reward, and you can think of the game as an environment that the model is exploring. So Emily, I hope I've answered your question. If there's anything, if there's a follow-up or any such thing, you may feel free to ask me again in the chat. All right. So how do we reward a computer? It surely has no concept of good or bad. That's a really great question. So you reward a computer by giving it points. So when you're playing a game, what do? You're playing a game, you make certain moves, right? So when you make these certain moves, based on your moves, you'll be getting some points or you'll be losing some points, right? So that's how we reward a computer. In basic sense, when you take it as game theory, we'll reward a computer by like basically increasing the point value or decreasing the point value. Now, when you look into reinforcement learning, there are a variety of different applications that it can go for. So when you think about all these different applications, the way you reward it could be different. So the points need not just be, just plus or minus. It could be something like, it could be some other type of value as well. But it's mostly these type of numeric values that are given. So that's how you reward a computer. Hope that's answered your question. Okay. I think maybe I'll take up one more question, and I think after that Shrishti can continue, and we'll be typing out the remaining questions. So, what algorithms are used for reinforcement learning, like supervised and unsupervised? So yeah, so you have different types of algorithms for supervised, unsupervised, and reinforcement. So for supervised, let's say you have like regression, classification type algorithms. Now for unsupervised, you will have something known as clustering. So clustering is basically like I mentioned, you have some data that you know nothing about. What your job is, or what the machine's job is, to find the similarity in this data and group it based on the similarity. And for reinforcement learning, there are a variety of other different types of algorithms that basically help the agent, that is the model, go through its environment and learn on the basis of trial and error. So if anyone else has any other points to add in, you may add them in the chat. And if the participants' questions are answered, do let us know in the chat. If you have any follow-up questions, please feel to ask again. And I think we'll be moving on. So we see a lot of other questions, so we'll definitely be typing them out in the chat as well. So yep, that's all from my end. Shrishti, I think you can continue.
Okay. So I hope guys that answered your queries. And now it's time for some questions and some poll time. Okay. So the first question is, a man is learning to cook. The first few days he suffers multiple burns and cuts, but slowly he becomes better. In a few months he becomes quite comfortable with cooking. If this situation was mapped to any type of ML algorithm, ML method, then what type is it? Okay, most of you have already answered. Okay, so guys, you can think of it as this man is trying to learn on its own. The he is suffering from burns and cuts, but he's still trying to learn uh he's he's still trying to learn cooking, and the moment he's comfortable with it. So okay, shall we go to the next question and then open the poll? Okay. Okay, this question is, an owner of a company wants to release a new product, but is quite unsure of what his customers enjoy. After multiple surveys and a lot of research, he finds out that 70% of his customers like stationery, 20% like electronics, and the remaining 10% like furniture. Based on this, he decides to release new headphones. If this situation was mapped to a type of ML, then what type is it? Okay, some mixed answers I'm seeing here on the chat. Okay. So one hint you can answer in the poll, guys. The poll is up. Okay. You can think of it as, here there is nothing to predict. So that's a hint for you. Uh, if you see that after a lot of surveys, they have found out that okay, this percent of customers, they like stationery. So this group of customers like stationery. This number of people like electronics, and the rest of them like furniture. So how, which ML algorithm can you closely relate this situation to? Okay. Okay. The first one, most of them answered the correct. The answer is reinforcement learning for the first one, because you see here there is nothing to predict, right? There is no labeled set that we are not telling the man this is how you have to cook or something like that, and there is nothing that he's trying to figure out, or maybe there is nothing he's trying to group or finding similarity into. He's just trying to learn on its own based on his experience. He's trying to learn, right? So the answer would be reinforcement learning. And the second one, okay, there was some people answered it supervised learning, but the correct answer is unsupervised learning. Just as I said that here in this question there was nothing to predict it. From the survey they just found out that this these number of people liked stationery, these number of people liked electronics, these number of them liked furniture. So they just created segment of customers who liked stationery, electronics, and furniture. So it's like grouping them, finding similarity. 70% of them like stationery and so on. So this will the correct answer will be unsupervised learning. Okay, let's move on to the next part. Okay. Okay. So basically, how do we implement uh, uh, machine learning? It's just that we give the data, we create a model on that data, and we deploy the data. That's the overview of how ML works. There, can you move to the next slide? So here you can say to the model, we give the data and we choose based on the target variable. We can see, or based on a situation, we can see what type of algorithm and what type of, firstly, we need to see what type of ML method we're going to use. Is it supervised, unsupervised, or reinforcement? And based on what type of target variable it is, then we can choose whether it's regression or clustering or association or classification. So that is how we create the model. Then after several uh, model training, we can deploy our model to production. So this is basically how the data set that we are providing to the model, to our algorithm, this is how we split the data. This is basically a structure, you can say. We can divide the complete data into these three sets: training set, validation set, and the testing set. So training set, as I already described, is basically what tells the model that this data. Basically, the model tries to learn from this data, whether it's labeled, unlabeled, or anything. Then the validation data set, you can think of it. It's basically a part of a training data set. We'll see later how. So validation data set is like basically used to fine tune the model. You don't uh, really ask the model to learn from it directly. It's not exactly the same as training set. Basically there are various parameters with which we can fine tune the model. We can evaluate our model's performance with this data set. And lastly, we have the testing data set. And from this data, it's basically how we check whether our how accurate our model is performing. Can we go to the next slide? And yes, you need to be sure that your data is properly cleaned, because if it is not cleaned, then your model is not going to perform well. Okay, so this is just overview. Like, this is a repetitive process. You can see here that we train the data, we evaluate the data. If the performance is not good, we can again train the data, again evaluate the model. Once we feel that the data is predicting, basically performing with the uh, good probability or good accuracy, we can then test our data on the testing set. Next slide. Okay, this is a type of validation that we do. So you can think of it, there is basically, as I told you, that validation set is a part of training set, and the test set is a different set. That is a complete foreign data set. We don't allow the model to see it, or we don't provide that data while we are training the data, while we are training the data, we don't allow the model to have the look at that data. So basically, can we go to the next slide, Sneha? The image would be a better way to explain. Okay, here you can see the first slab. If you see, it's like the original data set. Suppose we have 100 records of that. What we can do is 70% we can take training set and 30% we can take the test set, and we keep the test set aside. After our model's accuracy is good enough, we can give the test set and we check how accurate our data is, our model is. So with this training set, what we do here, we have suppose 70% of that. What we do is, for the first iteration, we will train the model on 60%, like 60 records of that. Okay, the 10 records remaining, we can validate the model on those 10 records. And if it's performing not well, what we can do is just take the other part of the data, and the remaining enough, we can take it as training data, and we can change the validation set. This is how we can perform multiple iterations on the training and the validation set, just to improve the accuracy of a model. Once that is done, we can finally move on to the test set, just to check the performance of that. Okay, so that's it, I think. Are there any questions, guys?
Shrishti, could you please repeat validation set? An attendee has asked you to just repeat.
1 second, just a second. Okay, sorry for the inconvenience. Okay, so basically, validation is like you evaluate the model on that unknown set of data. Once, if like 60 records, on 60 records, the model is trained on. The rest 10 records, we try to evaluate the model, whether it's working fine or not. There might be some unknown things which the model does not know. So with the help of this validation set, we can check whether the model is performing well or not. If it is not, if the score is, there's a way you can check whether your model is working fine or not. There's this accuracy score. There are different ways how you can check the score of your model. So based on one iteration, if the score is not good enough, you can run the second iteration, and you can take uh, uh, that validation set, you can include in your training set for the second iteration, and take the some part of the training set to the validation set and check if it's working fine or not, if the performance is good or not. Similarly, you run iteration so that all of the parts of the training set are taken as part of that validation set. It's a type of validation that we do. So there are other types as well, so we can explore that later on. I hope that clears your doubt. Okay, I think we can move further. Okay, over to Julia.
Thank you, Shrishti, for the amazing content covered. Together, we're now going to move on to two very important concepts when we're working on machine learning projects, which is bias and variance. And I'm sure you've heard of it if you've worked on a machine learning project before. So bias is the difference between the average prediction of our model and the correct value that we're trying to predict. It basically means how much off our predictions are from the actual data that we were trying to predict. So as you might guess, when we say that our model has high bias, it means that the model pays little attention to the training data. So the predictions are very off from the actual data and oversimplifies the model. This is going to mean that when we're trying to predict also the training data values, we're going to have a high error. And also when shown unseen data, we're going to have as well a high error. Next slide, please. Yeah. But we now can have the complete opposite side of this, which is variance. And variance is the variability of the model prediction for a given data point or a value which tells us how spread our data is. So if our model has high variance, it means the model is paying too much attention to the training data. So it's learning the training data perfectly and does not generalize enough in order to perform well on unseen data. So this means that we perform very well when we're trying to predict on training data because it has learned it perfectly. However, when shown unseen data, when going to data it has not seen before, it will actually have a high error. Next slide, please. So as you might guess now, we're trying to find some kind of balance between the two and find the middle ground when we cannot have a very high variance or very high bias.
Sorry, Julia, someone wants you to explain bias once again. So I'm just going back to that slide.
Okay, perfect. Bias when we're trying to do a machine learning project, we're trying to predict values. Basically, we have the X values, the training X values, and we have the labels, the Y's. There are the actual values and the actual predicted values that our model predicts. And the bias is basically what is the difference between the actual values that we were trying to predict and what our model actually is able to predict. I don't know if this answers you. Also, we're gonna have a graph on both of them, and I think that also helps a lot to put things a bit into perspective. If you can move on to the next slide. Perfect. So as we said, now we want to find a perfect balance, a model that does not have a very high bias or a very high variance. So as you can see, here we can look in the graph that we have at the very left, and we see that we have a very high bias, but a low variance. This means, as you can see from the graph, that the model complexity is too low. There is very few parameters in the model. This means that the model does not learn the training data enough in order to generalize. And we said when there is a high bias, it will perform bad on the training data because it didn't learn it enough, but it will also perform very bad also in unseen data because it doesn't catch the main pattern of the data set in order to be able to do very good predictions. I don't know if there is any questions, let me know. But also it can be the opposite side of it. If we look on the right part of the graph, now we're going to have the complete opposite. We're going to have a high variance and a low bias because our model is now too complex. There is too many parameters. It has learned the training data too much, too well, that is not able to generalize enough. In this case, this is also bad because as well, it's going to perform well on training data, but in the real world, when we're trying to show it unseen data, that is when it's not going to perform well, and we're going to have a very high error on unseen data, which is something that we don't want. So as you can guess, we want to find the middle ground between the two, some perfect optimum complexity of our model in order for the error to be at its lowest. Next slide, please, now. As you can see, we have the graph of the variance, the bias, and the total error. The total error is something that we want to put as close to zero, although as for now, it cannot never be zero because we still have the irreducible error, which the irreducible error is mainly error that comes from the noise that the problem has itself in the data. So it's impossible for that to go to zero. But in order for us to have this minimized total error, we need to find a very good balance between the bias and the variance. And the total error is the sum of the bias squared, the variance, and this irreducible error. And as you can see in the graph in the middle, we have this zone of optimum model complexity. When we're going to have the perfect amount of parameters, not too to generalize enough the data in order to predict the pattern, but not learn it too well that when shown unseen data will perform badly. So at this point, I would like to take any questions.
Um,
I think, Julia, you can maybe check the Q&A box. There are a few questions related to bias and variance.
No, for my understanding, there is no bias and invariance in the case of reinforced learning, because it would be, and please anyone else, like feel free to jump in, but we'll have to have the X values and the Y values in order to see, for example, the bias, how much off our predictions are from the actual value. And the bias squared, because we're talking about, as always when we talk about errors, we never talk about the error itself, but it's just the way that errors are explained from the actual values, also in math, from the actual value to the predicted one. If there are no more questions for here, we can maybe move on to the next slide. So just to give a bit of the bigger picture now for all the steps we have to go through in machine learning. First of all, we have to gather the data that usually you can like either gather yourself, or when you're doing a machine learning project, you can like find data sets online. The second step, which is very important, is to prepare your data. And especially when we're working with real world data, it's very unfortunate, but most of the time is not going to be useful as it comes, but you have to clean it, look for outliers, look for noise, for general patterns that will preparing the data is a huge step that's going to help you in choosing the model, then having the model and predicting. Then the third step is choosing the model, which the model you choose varies on the data you have, on what you want to predict. And then you start training on the training data set and start evaluating, as we saw on the validation data set as well. And then there's like this key step of hyperparameter tuning, which don't worry about it too much right now, but there's a lot of different ways to do that through grid search, through random search, Bayesian optimization, which we're not going to get through at this point, but definitely come to our next series and you might find the answer. And also at the very end, after we've gone all through all the steps, then we can have, we can make a prediction. We'll have a model that we will be able to predict on values and on data that it has not seen before. There are some questions. What tips do you have for a live coding interviewing pattern for data science role? Would they prefer supervised and unsupervised when reinforcement learning type of problems? From my experience, you definitely will have to also look at the company itself and what they work on and the project you will have to work on. But definitely, like what I've experienced more is like they come questions for both of them. So my suggestion would be to definitely prepare for both of them. And I think someone else answered the other question. Okay, so now we are at two very important concepts in machine learning models, which are overfitting and underfitting. When we say that our model is overfitting, it means that it has too much for one situation only. For example, if you're trying, let's say, you have an exam the next day and you really want to do well in that exam. So the professor gives you a practice exam and you're like, I'm going to learn everything to do the practice exam very well. So you learn everything that's in the practice exam, do it very well. Exam, some topics you maybe didn't cover in the practice exam, now you're going to perform badly. And that's exactly what overfitting means. It's that the model, the machine in this case, learns too much about the training data, that it also learns the noise involved as well. It doesn't generalize enough. So it performs it has a very high accuracy while in the training data set. However, when it goes to the actual values we want to predict to the test data, we'll have a very low accuracy. Or in our case, when it goes to the actual exam, we'll have a very low accuracy. And this can be mitigated by reducing the model complexity and increasing the training data. I saw a question in the chat. Oh. If you have questions, please post them on the Q&A. As I said, this can be mitigated by reducing the model complexity, so making the model less specific to the training data, making the model with less parameters, or increase the training data set, because if you increase the training data set, it's more likely that the model is not going to learn the noise of it, but it's going to learn a more general pattern, because it's going to have more data to learn from. But on the other side, we have a case of underfitting. And let's say that I don't really want to ace this exam. Like, I don't practice too much on the practice exam. So I don't learn even the things that are in the practice exam too much. I learn too many general stuff that I'm not going to perform well on the practice exam, but also in the actual exam that the professor is going to give me. The same thing happens with machines. The model will be unable to understand the general pattern and capture the underlying pattern in the data set. So when it comes to predicting values for the training data, we'll score very low, but also have a very low accuracy for unseen data, because we cannot have predictions that are accurate for either side. This can be mitigated again by increasing the model complexity, so increasing the parameters of our model, and by removing the noise in the data. Next slide, please, Sneha. Like here, I think everyone can understand it better, the case of underfitting, overfitting, and what we actually want. Let's say that we have this case that we want to separate the purple stars from the green points. And now we, for example, we start by having our model is always going to be shown in red. And first of all, we want our model to be, let's say, a line. So we want to separate the stars from the points with the line. And we see at the very first graph that the line is very generalized. It has a very high bias, meaning that there's so many points that we have actually misclassified, so many green lines that are on the side of the stars and the opposite way around. So in this case of a high bias, we're going to have a high training error, but also a high test error. So let's say, because this line is too general, now I want something that's a lot better. So I go on the right side, on the right graph, which we have a case of overfitting, which we have like this very squiggly line that we try to predict everything perfect on our training data. Like here we have all the stars predicted very accurately and all the points predicted very accurately. However, this is going to have a low training error because it's almost perfect. However, it's going to have a very high test error because when it's going to see unseen data, there's going to be some kind of noise that this is not general enough for it to perform well. So we want something more in the middle, something that will be able to understand the pattern that they are separated, but also not understand it too much in order that when it sees unseen data to perform badly. And that's when the optimum comes, and it's the graph in the middle, when we actually choose for our model to be a hyperbola, which will separate them good enough. Definitely we have some points that are misclassified, but still this is going to help us have a low training error, but also low test error, because if this is the pattern, when it's going to see new data, it's still going to be able to predict them fairly accurately. I'm going to take some questions. What are the techniques to remove noise from the data? This is also a lot when we do prepare our data. We definitely we would like to look for outliers, for example, when you see that there are values that are too off. Because like whenever you do like real world data, there can be like a mistake in how the data is gotten or anything that can have these outliers in your data that's going to prevent the training data set to be something that we can get a generalized pattern that then we can be able to predict and to create, like, to train a model that will be able to predict some kind of like same pattern data. So that's why it's very, very important to clean your data before starting. Underfitting, low accuracy in both training and accuracy. In both training and I guess testing, does this not lead to the conclusion there is both high variance and high bias when it comes to underfitting? I'm not really sure about the first question. If you can like maybe explain it more, because when a model underfits, it means that it has a very high bias. Like our predicted values are going to be very off from the actual values we want to predict. So that's what it will mean to have a very high bias. Looks like miscategorization is worse in the optimum graph compared to the underfit one. Can we go, okay, we are in the slide. I shouldn't say that's the case, because if you can see the general pattern of how the stars and points are aligned, they're kind of aligned that the stars are like in the form of a hyperbola, and then the points are more on top of that. So if you think of like a bigger data set or like data that is not seen before, it's very likely that it's going to have the same pattern if our trained data set is actually good and it's a good representation of the overall data set. So if it's in a bigger data set overall with a line, definitely if the pattern is in a hyperbola, the line is always going to have the biggest error. If there's any other questions or anything else that anyone wants to point out. If not, we can like move to the next slide. So now we have a small quiz for you guys. The first one, it's bias and variance trade-off in overfitting. So what does it mean when what do we have high or low bias, high or low variance? And the next one is going to be, next slide, please. The next one is going to be the same thing, but in underfitting. If we have, what does it mean that we have low or high bias or high and low variance? So please, if we can start the poll. And I'm going to give you guys a couple of seconds for you to answer. If enough people have answered, I think maybe we can stop the polls and give the answers. If we can see the results of the polls now. Okay, so perfect for the first one, which is overfitting. As we said, for overfitting is that our model learns too much about the training data. So it's too many parameters and it's going to perform good on the training data set. So the high would mean that actually has a high variance, meaning that has learned the variability in our training data set the best, but it's going to have a high variance and low bias, which I think almost like 50% of you guys answered the correct one. There's a lot of, I think, mistaken with high bias and low variance. This would be the other case of the second poll that we did, which is the underfitting. In underfitting, as we said, there is a high error everywhere because the model pays too little attention to the training data. So it's not complex enough to be able to understand the pattern of the training data. So it's going to perform bad on the training data and on the test data. It means that the predicted values are going to be very off from the actual values that we were trying to predict. which is going to mean that it's going to have a very high bias and low variance because it doesn't learn the variability in our data set enough. So for the first one would be the first answer, a low bias and a high variance. And for underfitting, it's going to be the opposite, the third answer, which is going to be a high bias and a low variance. So if there is any more questions, I know someone asked for a single good book source for beginners to learn more about machine learning. I cannot remember the name of the one that I learned right now. I definitely, if someone can add it in the Q&A, but also if you join our Slack channel, we definitely ask there. There's so many people that can help you answer that question and can give you a lot of suggestions on very good books to either get you started or to prepare you for interviews for data science jobs. So if there is no more questions, and I think more questions are being answered as well, I can give the word back to Sneha. Yes.
Sorry, Julia, would you mind explaining the second question again? Because there was, okay, I think it's been answered, but there was a question about the bias variance trade-off in underfitting. So if you could just explain that once more. So
okay, perfect.
In case anyone has to speak.
Yeah, when we talk about underfitting, as we said, is that the model pays too little attention to the training data, pays too little attention to getting the generalized pattern of the data set. It means that if it pays too little attention, we'll not be able to predict well, not the training data, nor the test data. It means that the predicted values that we're going to have from our model are going to be very wrong, very far away from our actual value that we wanted to predict. And as we said, the bias is this difference between the actual values that we want to predict and the values that our model predicts. That means that it's going to have a very high bias. And on the other side, a very low variance, because variance is the variability of our data set. So it's not going to learn the variability in our data set enough. It's not going to learn the general pattern in our data set. And it's going to perform, as we said, bad on both training and test data set. I hope this helps a bit.
I think that was really clear. And
okay, word back to you, Sneha.
All right. So yes, with that, we've come to the end of this introduction session. Thank you so much, Shrishti and Julia. You guys spoke really, really well. And I think the speakers will be open to taking questions now. But before that, I just want to give a shout out to our entire team. They've put a lot of work into this, taking care of the graphics, taking care of these slides, taking care of moderating the chat, as well as questions, taking care of gathering content for these slides, and the wonderful, wonderful speakers who basically led the session today, and our wonderful leads, Stephanie and Zareen, who are basically the backbone of this entire process. So I just want to give a huge shout out to everyone here. All right, so we'll be open to questions now. And if anyone has any questions, feel free to ask in the Q&A box so that it's clearly visible. Yes, the slides will be shared. So you can join our Slack channels, and that's where slides and extra resources will be shared. Julia, maybe would you like to take up this question? There's an attendee who's asked, could you explain variance with an example? Hello?
Sure. Like we might like go back, for example, to our previous example that we had for the exam, and like how we're like trying to like learn everything perfect in the practice exam. I think to me that happens a lot in college, that when the professor gives me a practice exam, I try to learn like everything that is in there. So, like I try to learn all the variability of the questions that are in the exam. So I learned like, all of them perfectly, and I put all my effort in learning them. So I learned like all the different like topics that he puts in there. But when we'll like come into like the actual exam, I have overlearned perfectly the practice exam. So I've learned like the complexity of my learning is too high. Like I've learned too much about the practice exam itself, about the practice questions itself. So when I will come to like the actual exam, I'll have like different questions that are outside of this one that I have in the practice exam. But because I've like learned too well only the practice exam once, I've like focused my learning too much on those. Now I'm going to perform poorly on the actual exam because I've not learned it generalized enough in order for me to perform well on both of them. I hope that answers your question.
Really great explanation, Julia. So I really hope that answered your question. If you have any follow-up questions or if you want us to explain it again, go ahead. Julia, so they're asking which one of these is low and high variance. I think with respect to this graph.
To this graph? Okay, perfect. So if you see on like the very right side of it, we have the variance shown in like kind of blue. That's where the high variance will be, because as we said, the model complexity is going to be too high. We're going to have too many parameters in our model. The model is going to learn the training data two-way perfectly, or like us, we were going to learn the practice exam too perfect, all the questions. So it means that now we have learned the variability of our data set way too much. So as you see in the graph, there will be the very right, the right part of it when the model is too complex and we have a large number of parameters. And as we see there, of course, the error is going to be high because when we're going to show like unseen data or like unseen questions in our exams, now we're going to perform poorly and have a bigger total error.
Great. Thank you. So just to maybe like sum it up, bias is when you're like way too lazy. Like you're just like, you don't want to learn anything and you've oversimplified things. Things are supposed to be a little bit complex, but even that you've just completely oversimplified it. So when you do in that case, the model really doesn't learn much. So that's what with bias. And variance is basically like what Julia was saying. You've done way too much. There's just too much that you've done. And variance also is a parameter that can decide how well your model responds to different data. So if like with one set of data, you're getting a good accuracy, then you're given some other set of data, but you're not, but like, you know, the accuracy really changes. That means that you have quite a high variance. So yeah, that's just to sum up whatever Julia's mentioned.
Also, please feel free to like message us on our Slack channel. I'm sure like all of the participants will be very gladly to answer any questions as well, or like feel free to message us directly as well if you have more questions at any time, or you need any like suggestions, or you think we might help you in any way in your learning of machine learning.
Totally agree. Would the speakers like to take up the remaining questions in the Q&A box? There are 2 questions. So, Shrishti, you can also feel free to answer.
Shrishti wants to answer those 2 questions.
Okay, Julia, you can do it. Fine. Oh, okay. This one, how will you divide the original data set into train and test with? Yeah, there is like, there is obviously some proportion in which you divide the training and the test data set. So that is basically a part of how you write the code. When you're writing the code, that is a later on you learn how to actually divide it when you're actually writing the code. So there's a part, there's a 1-line code where you actually write that this percentage of data will be training set and the remaining will be the test set. That is how you divide. And this I'm not sure if you can elaborate on the question. For the test and validation, are they sequential or simultaneous? As far as I understood, I think it's like there are actually different ways you can do validation. One of them is cross-fold validation. There is cross validation. There is k-fold validation. There are different methods in which you can validate your model.
Also, like I would say that for a lot of projects I've been working on, it's like very it's pretty common to allocate, for example, 80% to all the training and validation data set and leave like a 20% on test data. And going back also to the first question that is in the Q&A, it's very, very important to always separate the training and test data before you start training the model, because it does happen. I think it has happened to everyone, like getting started in machine learning, to train your model on actually the test data. And then you look at the very end of the predictions and you see that you have a very high accuracy for both of them. But that might be because you tested, you trained the model in your test data. So the model will learn from your test data as well. So it's not going to be unseen data. And the accuracy of our model is actually seen on unseen data. That's the main goal is to be able to predict on data it has never seen before. So it must not be trained on the test data. I think
people like when I also started with machine learning, this is a very common approach that Julia stated. Like first we train the data on the whole data, and then you get a nice good accuracy for the model above 90, and it's like 100, and you seem to be very happy. But don't get so happy. Go through your code again and check that you have splitted your data first before actually training it.
I think those were like really, really perfect answers. And I hope you've understood why you need to basically keep the training and the testing data separate. You do not want to test them exactly on the trained data because they obviously do very well on that. So when you suddenly give them new data, they'll not be able to, the model will not be able to do very well. So I think like both Shrishti and Julia really gave perfect answers for these. So I think we have a few more questions. Yeah, I think both of you can split it as per you.
Here's a question I think about bias and variance. Is bias in model complexity the cause of real world bias in machine learning algorithms, facial recognition to be one? Or is that bias more due to the training and test data not covering a diverse enough data set, or also because historical data already contains bias or it is simplified? That's definitely a big problem in machine learning is the data sets we provide. And I think we probably refer to the same one when we talk about facial recognition and all the, I guess, the backlash that machine learning sometimes does receive for the bias that it has. As I understand your question, bias would be, bias is it's the difference of how much off the predictions are. So is that bias more due, do you mean is high bias more due to training and test data not covering a diverse enough data set, or a low bias?
I think what they're asking is, so basically here, the bias is to say that the model is not complex enough to understand your data. That is, you've oversimplified the model. The model is lazy. It's not able to recognize the patterns in your data. That's the bias here we're talking about. But this bias is different from the human bias that you're talking about. So I think that's what they mean. This person means, Julia, like this, the bias that you just spoke about versus the actual bias that's there in data set. So you're right, that bias is more due to the fact that we do not collect diverse enough data. Maybe our data is skewed or it's towards one particular faction rather than covering the entire or different types of parameters. It's towards one particular faction. So that is a different kind of bias. That is, your data is not diversified. So that is where that bias comes in from. And this bias that we're talking about is that the model is not complex enough to basically learn the patterns in your data. So I hope that answered you, Corina.
Yes, also I want to add that in every machine learning project that you start, one of the key points would be to try to find a data set that is as small, covers all possible scenarios. That's a very I think big problem sometimes in machine learning is the quality of your data set, how much it generalizes the all sample that you also will try to test on and try to predict. So the better data set you'll have, the better predictions you'll have.
And Okay, that question disappeared. There was this question: how do you determine the value k in k-fold validation? It's generally up to you, but we minimum is 2 we should take, and maximum could be the number of records you have. But that is like too tiring. I mean, if there are 1,000 records, you can run that training and validation up to 1,000 times. The value of k could be 1,000, but that depends on you. That is, and there was one question, I think. Is splitting necessary before analysis? I think I don't think it's not necessary before analysis. Just before creating the model, you have to split the data.
Hey everyone, I just want to mention one point. Please do join the data science and Python Slack, and in the data science Slack, do ensure to join the ML study group channel, because that's where all the speakers are present, all the hosts and the leads, and you can always ask any other questions you have over there. And you can also gain suggestions, and basically any question you have about this series or about machine learning in general, you can put it up to the speakers there. So do join the ML study group series channel. So I think there's just one more question if any of the speakers want to answer.
Is there a Coursera course that you all like on machine learning? I can't think of one right now.
I also don't remember right now. Maybe if we can, if you join the Slack channel, maybe we can post links of that. We can do that, because right now we're not sure which one to think about.
So as for me, I'd recommend Andrew Ng's courses on both ML and deep learning. So ML is just one single course by University of Stanford. And for deep learning, it's a specialization. So these really explain a lot of concepts. So would definitely recommend that.
Yeah. Same. Andrew Ng is great, especially the deep learning course. I think it has helped me a lot. So definitely check it out if you have the opportunity to.
His Python course is really good. It's a specialization, like 4 or 5 courses in that specialization, and it's a really good one. And actually, it covers all the things regarding Python for data science. You can definitely go for that.
All right, so since we're running short of time, I think we'll be stopping our questions over here, but please do join the ML study group channel in both the data science as well as the Python Slack. Zareen has recently just shared the link for the same. So you can feel free to ask all your questions there with regards to this session, any other session, and we'll definitely get it clarified. So I think we should just take this one question. Yeah.
Feel free to reach out at any time to any of us directly on the Slack channel. We're all here to help.
Julia, there's just one bias variance question. I think we can just close with this.
Okay, perfect. I understand bias for less complex model. Please explain why the variability is less for less complex model. Because variability is like how different how much variability there is in our training data. So if we're trying to get, like always when we're trying to get a machine learning model to learn, is the general pattern. So if we now like try to learn too much of the variability, we try to like learn every specific thing about our data set, like the more we get the highest variability. As for here, like we have on the third graph that we have this quickly line, like it has learned it perfectly. It's learned the variability at its maximum, and it's going to be great for training data set, and it's definitely going to perform well on data it is already seen. But in the real world, when we actually want to predict like the data set and the data points that it has not seen before, it is not going to be general enough. It's not able to catch the general pattern enough to perform well on unseen data, because the model is too complex. It has too many parameters. It has learned the training data way too perfectly to be able to have the generalized pattern and perform well on unseen data. I really hope this helps.
That was really perfect. And I understand that, like, for people who are very, very new to machine learning, bias and variance, overfitting and underfitting can be a little confusing, but please don't worry, we'll be sharing resources in the Slack channels. So please do join the Slack channels in both the data science as well as the Python Slack, yeah. And do join the ML study group channel. So that's where all the speakers will be there. So the links for everything's already been put up in the chat. And I think we can close with that for today. Once again, thank you all so much for your wonderfully insightful questions. And thank you for being such active participants. Huge shout out to Julia and Shrishti for carrying through this amazing presentation. So thank you so much.
Also, thank you, Sneha, for hosting this session and for all the great work that you've put in the series.
All right, I think we can end the session here, Zareen.